So we should be live, I guess. Uh, you can tell me if you hear me or if it's working. I don't know. We'll see. All right, great. I'm doing good. I'm doing good. I don't know if it's gonna be a disaster, so hold your expectation. We'll see. But yeah, we're gonna talk about control systems, software, and if you guys, if you guys have any questions, we'll try to answer those, and we're gonna play around a little bit in MATLAB and see if we can do anything crazy. Nice, nice. My internet connection is not the best in the world, so oh, perfect. So if it's working, great. I don't know if I don't know if the latency is really high or not, so we'll see how much delay there is. Great, awesome. So let's get started. So I haven't updated, like I haven't filmed any updates on the channel. Like I've been working behind the scenes on the software, the control systems. So I can show you guys around the simulations in Simulink. And if you have any question, we can just answer those, like I said. All right, perfect. So let's get started. So you most of like what I'm gonna talk about is like it's gonna just like sort of repeat what Joe said on his channel when he was building Sprite on you know full state feedback and like uh, different types of controllers for guidance. All right, perfect. So what we have here is a simulation for my craft. So it's a brand new simulation. I just started working like a month ago, and I've slowly been like working on it and trying to get it to work. So what we have here is like it's LQR controller with like all the states. And I can just run the simulation and it's going to show you what the craft is doing. Or I don't think you can see that. Hold on. I'm just going to, yeah. So let me just run the simulation again. So that's a simulation for a 10-meter hop with a craft. The craft is going to look like kind of like Sprite, like Joe Barnard sprites. It's going to look like it's going to be similar, but not exactly the same. It's going to be powered by propellers instead of an EDF. Two counter-rotating propellers, one on top of each other, and yeah, it's gonna be maybe slightly smaller. We'll see. But the goal is about the same. Just trying telemetry, trying different guidance algorithm, and trying to get really robust controller working. So yeah. So that's a 10-meter up with like a 2-meter divert, trying to go like to the right and then at 10-meter, and it's gonna last about 30 seconds from liftoff to touchdown, and it's gonna be really cool. I'm I'm hoping we can fly this summer. Maybe we'll see. But yeah, that's really cool. So I can walk you through the simulation here. So we have the craft dynamics block. It's actually a 6 degree of freedom Euler block. And the idea is that we have 12 states coming out of the block. We have every time we have 3 axes. So we have position, velocity, orientation, and you know rate of rotation. So like how fast we're moving, how fast how fast are we rotating around. So that's 4 times 3 axes, so that's 12 states. We're actually controlling only 10. I've removed, maybe 9. No, sorry, 10. I've removed the controller for thrust, like giving commands to the propellers, is going to be put aside, and is going to run sort of like a PID controller. Just because like I have feed forward, I have other stuff in here, so it's gonna be separate from the other main controller. So yeah, and so we have all the states. I have a subsystem block here for the state vector. It's a little bit of a nightmare, but yeah, that sends the 10 states to a matrix, and what we're doing with uh, with the state vector is multiplying by the K matrix. And actually, that's what's happening in the state vector is that we're taking the set point, and we're doing the set points minus the state, so that we get a difference there, and that difference is going to be multiplied by the K matrix. And then we send that to the craft actuators, and we send that over back to the craft dynamics in torque. So that's the idea. There are more to it, like the force vector. All of that is like broken out by itself in the simulation. And yeah, there are pitch, position set points, position dot. Every time I got this question the other day, every time you see a state dot, that just means it's like it's a derivative, and derivative in relation to time. So if we have position, and pos dot just mean it's the derivative of position, which is velocity. So that's it. And so yeah, we got some scopes on position, because I'm really focused on getting position right. So X position is just the altitude. So you can see we go up to 10 meters, stay there for 10 seconds, and then come back down to 0. And then there's the Y position. So we go positive 2 meters on the y-axis, I think, and then we come back down. We come back center again above the launch site. So yeah, that's pretty much it for the simulation. All of that is already in the software, so it seems to be working. I have some work to do on the state estimation stuff for like to get a Kalman filter into the software. Shouldn't be too hard, but like that's still something to do. And yeah, once that's done, most of it is just building the craft and flying it. So yeah, do you guys have any question? Like I don't know, on stuff? Do you have trouble on something or with control system? And after that, I can also show you the telemetry software I've been working on for the flight computer, sending commands and receiving data to show it on pretty plots. And yeah, that's also, the stream is going to stay on the channel and sort of work as an update on the things that like I'm working on. I only spend about like 30 minutes every week, so I'm doing great. I've had a week of exams, and so yeah, it didn't end up like as good as I wanted to be, but like I don't know, getting back to work after a week of exam. So yeah. So I started LQR in December, I think, and it started working like it only like it's not that hard to understand it, like how it works. It's actually implementing it. Like you can, there are a lot of videos online to show you like how LQR works. It's just understanding it, like how the main question is actually how do you implement it in MATLAB and then in your flight software. So that's it took me maybe 2 weeks, 3 weeks to get it to work initially, and then I had more work to do on the matrices, changing things up. And also, like, I can show you in MATLAB, I think, yeah, you can still see, I think, what I'm showing. So LQR, like, you have a few matrices you have to like build for your craft. So you have the A matrix, and actually, hold on, I can show you the matrices in Excel and show you what's happening, because like that's the true magic. Like it's really where LQR is interesting, because it's so powerful. You can do so many things. I just need to find the matrices in Windows. But yeah, it's hard to understand at first how they work, and it takes some time. But then once you understand what's happening on the craft and like in the control software, it's not that hard. It's just are you compiling the simulating to an Arduino or something? So I could do that. I could. There are a lot of tools in MATLAB to do that. I don't use them for now because I'm working at a very small scale. So like I write all the software myself, and so it's not like the software is not that big. There are like 1,000 lines, so it's pretty easy to just write them yourself. And it's easier to debug stuff because you already know what you wrote and how, like, it's easier to debug basically. But I could do that. Like if I ever do like more complex craft, I will have to do that. But yeah, you can of course do that. Oh, thank you. How do you plan to simulate your observer? Can you rephrase your question? I'm not sure I'm getting it. Like, are you talking about the state estimation, like trying to simulate the sensors in the simulation? And so just for the time being, so that's, for example, the A matrix. So you have all the states. You have x theta, y theta, etc., and then theta dot, position, and velocity. And you can see the x and the x velocity and x position are missing because I don't want to control those. And same in the other column. And that's, you can see it's to carry the gain forward. Oh, sorry, not the gain, the value. So basically, we're integrating the theta dot and velocity, which is just position dot, and we're integrating them so that we get the x theta and any theta state or any position state. So that's just the A matrix. That's what it's doing. Then there is the B matrix with all the inertia. It's actually the inverse of the. Please talk about your observer design. Can you define? Sorry, Brian. Can you like define what do you mean by observer design? Because I'm not quite sure what you're talking about. Yeah, just I can look it up. I'm not that great at vocabulary, and I'm not sure what observer design is. Sorry. But yeah, the B matrix is just to understand, like, you know how, like, you want to understand when you apply a torque to your vehicle, you want to understand how it's going to affect your state vector, and in this case, it's just the inverse of a matrix. Sorry, the inverse of the inertia that gets multiplied by the torque, and that gives you the theta dot. And then I think Yeah, the R matrix is just one gain because you can do multiple gain, I think, for the R matrix. In my case, it's just two because it's working. I think I tuned it, and two ended up being the right value according to a few methods. So that's what I chose. Then there's the K matrix. I'm gonna talk about that in a second. And then there is the Q matrix. So that's your preferences for the craft. It's like, for example, I don't want to be super aggressive on theta and theta dot. So you can see they are smaller than the other y and z. So like x is very easy to move around, and so we're just having very low gains in the Q matrix. And so once you have those matrix in MATLAB, let's get back to MATLAB. Yeah, there we go. What you can do is it's a simple command, LQRA BQR, and that gives you the the K matrix. So that's a 3 by 10 matrix, and then you can multiply that by the difference from the the set point minus the actual state, and then that gives you the commands. The states that cannot be directly measured. Yeah, so I'm gonna implement a Kalman filter. For now, like that's the part of the software that needs work. I need to implement that in the software. I'm gonna write a Kalman filter. I haven't looked too much into this right now, just because I had so much work with just the controller itself. But yeah, it's gonna be a Kalman filter. I think I'm gonna put in there, like, so you have the predict step and the update step. I'm just working through what a Kalman filter is, but maybe you already know. But basically, you have a predict step that's just a prediction using the matrices I show. I showed like the A, B, maybe C and D, I'm not sure, but at least A and B. And so and then you have the update step that just update the measurement with like the actual sensor readings. And so it's not yeah, that's pretty much it. And so I will have to simulate that in the Simulink simulation. That's going to be part of it. It's just not there yet. I don't have like I'm not simulating the sensors and the filter itself in the simulation yet, but that's going to come later. So yeah, and once we have the K matrix, we can create a system with SS A minus B times K. Yeah, K. K. I think it's B, C, D. And then we can do step of that system. And the idea here is that MATLAB is just simulating for us. MATLAB is just simulating a few steps on from that simulation, from like of a system, from like the matrices. The matrices basically describe the dynamics of a system, and once we know them and they're in the system, we can just run simulation from that, and that gives us like a response curve. And other people like to plot them on a pole zero map, and yeah, we can just do that. Oops. And the pole zero map is actually pretty helpful to show you the reaction of the systems, like how it's going to react to different disturbances. And yeah, you have like an imaginary axis and a real axis. One represents the pole of the system and the other the zero of the system. I don't remember which one it is. I think the real axis is going to show you the zero, and the imaginary is going to show you the poles of the system. But basically it gives you an idea of how aggressive it's going to react for some states. I don't remember which states are which zero and poles, but yeah, that's the idea behind all of that, behind LQR. And the good thing about LQR is that it's sort of like, in a sense, I mean, in a sense, it's like, in my case, three controllers, three PD controller, actually torque PD controller, because as you can see in this subsystem, we're taking the COM to TVC distance and we're dividing it because we want to find the actual torque that we're going to apply to the rocket, and we need to know the distance between the center of gravity and the TVC. So that's what we're doing here, and that's very helpful because, like, if a thrust changes during the flight, we can the controller is robust for that. It's gonna be capable of modulating the responses that it's gonna send to the servo based off that. Based on the thrust, basically. And also, I think we can also implement feed forward for the inertia and stuff like that. So yeah, it's pretty it's quite robust, more than an orientation PID, especially for controlling position. That's really helpful. So yeah. I feel like that's about it for the simulations. If you have any question, I can again answer those. To be honest, like, I'm not I have an understanding of what's happening, but I'm not like a professional control system engineer. So like, I can try to answer the questions, but like, I don't know. I'm not the expert at control systems. So yeah, that's that, and then I can show you the software that I built for the. I mean, I didn't build the software. I built the interface for the for the telemetry. Yeah. All right. Let me switch view. There we go. So that's the. So here is the software for telemetry for the flight computer that we're gonna use. That's actually not the flight computer I have on my desk. That's an old one. That's not gonna cut it for what we need to do. But basically, I used it to get an idea of how I'm gonna implement all the telemetry stuff. And so you can see here we have multiple plots. We have the altitude, we have orientation, temperature of the altimeter, horizontal position, accelerometer. I mean, you can read all of those. Oops. Sorry, my camera just died because why not? But yeah, we have we can see what we're like. Sorry, we can basically have an idea of what the craft is doing while it's flying. And yeah, there are a few stuff missing here. I'm gonna have like I'm gonna do a sort of map to see like from above what the craft is doing in terms of position, whether it's going left or right or forward or back, and trying to understand if it's doing what it's supposed to do. So that's not Java. That's an embedded software. It's called Electric UI, and I don't think there is like a name for the. I can actually show you what it looks like in the software, but it's I've never quite seen that. Maybe it has a name. I don't know for sure. But yeah, it's called Electric UI, and yeah, it's quite pretty. I agree on that. And yeah, we can receive data from the craft. We can also send data to the craft. So for example, I have a button for the buzzer. I can turn on and off. We can reset position, start the auto sequence for launch. We can calibrate the IMU, abort, everything like that. So yeah, yeah, I can show you what it looks like. But yeah, if you go on, I think, I don't remember what's the name of the website. It's probably electric.ui, and they have some good examples of like what you can do with their software. Um, um, yeah, so that's what it looks like. So you can just yeah, I'm not gonna run through all of that because it's pretty boring, but yeah, we can create charts, buttons, everything that we want. We can create really good uh, mini application. I think it's really they made that system that sort of yeah, I don't know I don't know what it's called, but like I think they created this environment. Sorry, yeah, environment specifically for this sort of stuff with you know, trying to get data from a craft and interacting with the craft. Are you using separate microcontroller for telemetry? Uh, no, it's gonna be on the same microcontroller, which is kind of cursed, but like I think it's gonna work. I'm gonna use TNC 4.1 for everything, data logging. Yeah, everything is gonna run off of the TNC 4.1, and I think I saw one the other day. I'm trying to get a radio that's gonna work in I2C or SPI. It doesn't really matter, but just a protocol that is quite fast instead of serial. And I think with the 4.1, it's like I think the processor is gonna run at 600 megahertz. I think that's enough so that we can run everything off of the TNC 4.1. So everything on the same microcontroller, which is, you know, at what rate do you receive telemetry data on this telemetry software? I can tell you that. Hold on, I will check. Just 1 second. I think it's something like 25 hertz. I have it set in the flight software. Yeah, so it's every 50 milliseconds. So that's going to be, wait, is it? Yeah, so that's 20 hertz. So yeah, 20 hertz is how often we're getting telemetry from the craft. So it's already enough. That's like we don't need more. That's already good enough. And also like it's a sort of balancing act to try to not push too much telemetry out, so that we still have some cycles to like do all the state estimation stuff, and all the um, all the data logging without uh, keeping using too many clock cycles on the telemetry stuff, because it's not the most important stuff on the computer, even though that's part of it. So I can show you, for example, you can see we've drifted quite an amount. We no longer have the y-axis on the plot. There it is. But I can calibrate the IMU. So it's you can see also on the state plot, you can see the state. It went from 1 to 0, because 1 is when is idle state. It's when we're on the ground, and 0 is calibration. And you can see also the calibration progress, the progress bar, that gives you an idea of the progress on the calibration. So there we go. We went back to idle state, and you can see, yeah, now everything is calibrated. And you can see also the colors for each axis is the same everywhere. So blue is blue is X for orientation, accelerometers, altitude, and red is hold on, red is Z, and green is Y. So yeah, trying to be consistent in all the plots. So yeah. And yeah, that's going to be interesting. Also, I'm monitoring the delta T. Green is, I think it's state estimation. I mean, right now it's just doing quaternion calculation, and so it's doing that every 5 milliseconds. And then there is the red line, which is for just the cycle time for the general microcontroller. So yeah. We're missing a couple of things. Like I said, the map, the position map, and also a 3D render of the craft. When it rotates around, we want to see a 3D render of the craft. So that's still in progress, and we'll see. Maybe I can finish that before this, like by, I don't know, maybe by the end of April. We'll see. It's very slow progress. It's taking a lot of time to put everything together, and yeah, I don't know if, yeah, I've turned on the buzzer. It's pulsing every 2 seconds, I think. Yeah, it's pretty nice, and also having that buzzer switch is pretty nice for the neighbors when you're testing a lot your flight software. So yeah, yeah, that's pretty much it for the progress. And it doesn't seem a lot, but like I think total, like, yeah, I'm spending like 30 minutes every week working on that, and at the end, like, that's an amount of time spent on that. So yeah, yeah, and actually I can also show you, if I reset the position, you can see the horizontal position, altitude, and horizontal velocity all going to 0. And same for, like, if I start an auto sequence, you can see we're going to state 2, and you can see I have some amount of like set points already in the flight software. You can see that's the same profile that I show you in MATLAB. You can see the y set point moving. You're gonna have altitude, the x set point coming down for the landing. So it's already all in the flight software. Obviously, it's gonna be slightly different when we're flying. First of all, we'll do like a meter hop, like 1 meter high, and trying to see if I messed up something in the simulation or if everything is right. We'll see. But yeah, that's pretty much it. So I don't know if you have other questions about I don't know, simulations, control systems. Yeah. And yeah, I think someone asked, Boba here, you asked for the launch date. I don't know. I mean, to be fair, I'm focusing on the software first, trying to get everything to work. Same for the state estimation and the sensors. I'm gonna try to get you know, GPS chip for receiving data. That's going to be the U-Blocks. I think that's the Neo M9N, sorry. And yeah, I want to wait until I have all the sensors to actually do sensor fusion, because it seems like a bad idea to try to implement something that you can't test, because like it's not going to work for sure. Is the telemetry data used for analysis, or do you perform analysis on the data log in Flash? So, we're gonna store data on the flash chip during flight. Then it's gonna be sent to the SD card after the landing, and that's gonna be high resolution data. So like I don't know, 50 hertz, maybe 100 hertz, we'll see. But that's going to be, and we'll have a lot more information on the flash chip data. We'll store a lot more channel that what's happening in the telemetry software. But obviously, if something goes wrong during the flight, or we lose the vehicle, we'll have the data on the telemetry software. And actually, I'm gonna have two similar flight computer, one on the craft and one receiving the data on the ground. And so because they're exactly the same, I'm gonna be able to, when receiving data, store it as well on the SD card on the flight computer on the ground. That's gonna be linked them to the like my laptop. And so we're going to be able to also generate an CSV file from the data directly, not only like from screen capture on the laptop, but also like directly from the raw data coming from the craft in the air. So yeah, we're going to have some redundancy for all the data. This might have already been answered. What software are you using for the plots processing or something custom? So it's called Electric UI. You can see it at the top of the window. You can go on their website. They have like good rundowns of like like good examples, project examples for like this UI. And I did a lot of work in processing trying to get this to work. The only problem that I was having was that the plots were not time-based, they were sample-based. So basically how many bytes are coming in from the craft, and I wasn't a fan of that. I want things to be time-based. And so I and I tried modifying the library to do that, but it wasn't working very well. And I haven't. I should have probably checked if there was a better library out there for plots, but I ended up being contacted by someone in the BPS Discord, I believe, about that. And turns out I really like Electric UI, like the way it's set up. It's kind of weird when you get started because it's not what you expect when you're coming from processing. The language is really different, but yeah, it turned out to be, I think, a good idea. Um, do you just use a basic MATLAB and Simulink? Any add-on you recommend? I'm using the Aerospace Toolbox. I'm also using the System Identification Toolbox. I don't know if it's a separate toolbox or if it's coming with the the Aerospace block set. But yeah, yeah, I recommend the Aerospace block set because like most of the block I'm using are from the Aerospace block set. You can actually make those yourself technically. It's just more work for, like, for example, the 6 degrees of freedom block. You could you can just write the equations yourself into a custom block. Uh, it's just more work and yeah, I at least the aerospace block and maybe the one that has the system identification toolbox. That's basically the ones that you really need for any aerospace applications. Yeah. uh, yeah, I don't is the Zoe yeah, no, no, sorry, I'm mixing the uh, Zoe with the other GPS chip with RTK. But yeah, yeah, GPS chips are kind of expensive. Fortunately, I think the AMQ. I don't remember the price tag for that one. The M9N is actually, I think it has higher precision than the MAQ. Like the M9N can do like I think it can do like 2 meters or 1.5 meters and 25 hertz, uh, while the M8Q can only do like 20 hertz and 2.5 meters. But yeah, I was really trying to get the. I mean, like I think I made my choice. I just need to buy it now. But yeah, it's really hard to choose the right one because there are so many out there um, for your, like, it really depends on what you're doing. If you want really high precision, if you want high data rate or stuff like that. But yeah, also like sorry, jumping from one subject to the other, the layout for the uh, flight controller itself is progressing pretty well. I have a ton of modification to do because like uh, I'm learning as I go. That design, which was my first flight controller, sorry, flight computer, was really not the best one. There are so many things to change. But yeah, I have a ton of improvements to make on the new revision with all the telemetry and everything. It's gonna be crazy. Like it's gonna have like 10 servo outputs or something like that. Something crazy. Just like I don't want to be limited by the flight computer ever. So like I want as many channels as possible, as many like breakouts as possible. Like I mean not breakout, but like breaking out like all the pins of the processor, even if I don't think I'm gonna use them right away. I want them. I want to have like access to them. So yeah, the PCB design is going. I don't know. It's going not that bad. We'll see. We'll see if it works. But yeah, uh, I think that's about it for the updates. Um, I don't know if I've answered all the questions in the chat. But yeah, and I mean, I've also wrote the flight software again, like in February. I've started from the ground up again, and it turned out to be a really good idea because, like, I mean, the performances I'm getting from that new flight software revision are really good. Like you can see, it's pretty stable, and so yeah, it's gonna be fun to implement all the rest of the features in the next like 4 or 5 months. It's gonna be great, and yeah, we'll see if it works. Also, one thing you can notice now is now that the IMU has warmed up, you can see that the horizontal position uh, are not drifting that much anymore. I mean, it's still drifting, but like, yeah, that's pretty cool. So yeah, and also like there is a bit of a sorry, not common filter, complementary filter going on with the altitude. You can see the blue line is fusing the barometer and x-axis accelerometer. It's all also everything is in the inertial frame. Everything is rotated, so all the accelerometer you can see the blue line stays at 10 meter per second squared, no matter the orientation. So that's pretty cool. Oh, yeah, I might have broken something, but yeah, yeah, that's pretty cool to me. And so yeah, and I have a bunch of data to put in the telemetry software, like um, the commands to the servo and stuff like that. So we'll see how long it takes to implement everything. And yeah, next thing up is the Kalman filter, and once it's done, I need to finish the flight computer design, and that's gonna be pretty much it. And yeah, any any questions? I think that's all I have to say. So I don't know. Um, yeah, I don't know. I don't know what to say. Would you mind talking about rotation matrix from body frame to inertial frame? Sure, we can talk about that. So on the craft, on the sorry, on the I can maybe show you the bit of code in the flight software. I'm not gonna show you the entire flight software just because of, you know, I don't want people to use it, but I can show you how it happens in the flight software and then how it happened in MATLAB, because I'm using two different methods to do that. And yeah. Um, so in the flight software, here is the global acceleration quaternion. I should rename this and put it in a header file. But basically, we have the it's a matrix multiplication between the quaternion rotation matrix, and we're multiplying it by the state that we want to, sorry, the vector that we want to rotate it by. So we have the x, y, and z acceleration in the body, and we multiply this 3x1 matrix by the 3x3 matrix, the 3x3 quaternion matrix, and that returns the x inertial, y inertial, and z inertial. And that's pretty easy to do. It's just one matrix multiplication. And I can do that in the flight software because quaternion, we're using quaternion for the orientation stuff. And then in MATLAB, I'm using the rotation matrices for one main reason, is that all the axes here are, all the forces are local to the craft. The block returns, sends and expect local accelerations. However, gravity is not local; it's global. So what we're doing is that we're getting the orientation in this custom block, and then we have a few matrix multiplication. One to get to global, and once we're in global, we can add the gravity, the force of gravity. Right here, we're doing the mass times 10 or 9.81, whatever, and we're adding it to the x-axis. And once we have done that, we can use the rotation matrix again with the orientation, multiply that by the acceleration on the craft, sorry, the forces on the craft, and then we send that back to the to the 6 degree of freedom block. So yeah, that's this method is called DCM. We're using a DCM matrix, and in the flight software, it's a quaternion rotation matrix. So two different ways. The quaternion matrix is easier in a sense because you're not using cosines or sine, and you're not doing so many multiplication. Whereas the DCM matrix is a little bit, you know, is like it's quite a beef, and you have a lot of sine, cosine, and those can be really hard on the processor. So in MATLAB, it's fine to use the DCM matrix. It's actually easier. But in the flight software, it makes sense to use the quaternion rotation matrix. The random integer right here. It's to simulate wind. So I can show you, for now the gain is 0. So there is no wind in the simulation. So you'll see the y-axis is going to be really stable because there are no disturbances. So you can see it's really rock solid. The green line is the set point, and the yellow line is the actual position. And you can see it's you almost can see the yellow line because it's right underneath the green set point. So it's great. It's working perfectly. But in real life there is wind, and we need to simulate that. So right now there is nothing fancy yet. I will probably run some CFD and stuff like that to see with so much wind how much force we're applying on the craft, and once you know that force, it's going to be kind of easy to implement that in MATLAB. But for now, when I want to simulate winds, I'm going to just put some value and we'll see what happens. Yeah, you can see there is some wind, quite a bit of wind, and so you can see it's no longer straight. The craft is struggling a bit. Yeah, it's struggling quite a bit, and you can see, yeah, it's no longer matching the green set point. It's drifting because of the wind, and you can see the horizontal velocity control is not smooth either. It's really junky, and it's not smooth at all. So that's that's more realistic in the sense that there are disturbances in real life, and you want to simulate them as much as possible. So yeah, that's the random integer, and it's I'm using that random so that it's not smooth. It's not a constant. It's not a constant component of wind. It's simulating gusts and stuff like that. And so yeah, I just have a scope to like understand what's the force, and you can see you have a mean of like because you can set all the parameters in the block. So for example, the sample size and the sample per frame. Oops, sorry. Yeah. And you can see the output data type, which is double and stuff like that. So yeah, that's pretty cool. It's kind of stupid. It needs work. Like that's the most basic simulation you would want for full state feedback control. And yeah. So yeah. Any more questions on stuff like that? And I can show you the thrust controller too, which is you're gonna recognize a sort of PID approach with position and velocity, which is the derivative of position, so that's the PD aspect of things. And then there's the I term, integrating the velocity and position. So it's sort of a custom PID. And then we have some feed forward for the for when the craft is a little bit sideways, because when it's sideways, you're only getting a portion of your sorry, of your upward thrust component. So yeah. Flamey's deploy PCB looked like it had a couple of sensor boards stacked to the main board. Well, the next PCB. So yeah, for some of them, actually, so the IMU is going to be the BMI 088, which is full SMD. That's going to be on the board, so no breakouts for that one. I should try. Oh, I'm not going to have to do that for the SD card because the SD card is already on the TNC 4.1. So there is no breakout for the SD card. And then I will probably try to get the barometer also SMD, but I'm not sure. Maybe I will stick with a breakout, or maybe I will just say screw it and design an SMD for that one. So yeah, some components are I want to have a cleaner board because that looks really messy. Same, we're gonna change the 5-volt regulators to a buck converter to sort of mitigate heat on the board. That's gonna be something quite an improvement because you know the MEMS sensor on the IMU don't like differences in temperature. So we want to have like a very constant temperature on the board, and so the buck converter will generate less heat than the 5-volt linear regulator. But they're all gonna be like solder on manually with like hot air station and with solder paste. So yeah, that looked really messy. And same for the I don't know, all the resistance and yeah, everything is gonna be as much as possible SMD. But we'll see how it goes. Maybe it will cause more trouble than it's worth, but I think it's worth trying for now. I will just change the battery of the camera. Just 1 second. So yeah, yeah. So you can see there are a lot of things to change from Flyme. The flight computer needs to change. The flight software changes are in progress. The control system software improvements or changes are in progress. And then I need to design the crafts, and so we'll see how that goes. I think I have a good idea of what the propulsion system is going to look like, but it's like I need to confirm all the decision and choices. And yeah, I think like actually building the craft itself is going to take like a week, maybe like yeah, I can do it pretty quickly. Most of the components are going to be 3D printed in ABS, just to try to survive the heat during the summer, trying to not melt the components. And yeah, once I mean there are like still a lot of things on the to-do list, but I'm working my way there, and yeah, maybe it will fly this summer, and yeah. So yeah, other questions on stuff? I don't know. uh, um, yeah, I don't know. I don't have much more to say. It's been an hour. I don't know. Maybe you'll um, yeah, I don't know. It's getting weird. Um, and yeah, actually, like, also, I'm trying to not go too fast with the project because, like, I'm learning so much at the university right now that I can just reuse on the on making the craft itself. That I don't know if it's worth like speed running everything. I'm just trying to take my time and make a good decision, and yeah. So we'll see. Maybe it will work this summer or not. Yeah. I don't know. Maybe I will just leave it there, and yeah. I'm just making sure you don't have any more questions, but if it's not the case, I will probably just end the stream there because I don't have much more to say. Buck converters have a lot of switching noise, but proper filtering would save you. Yeah, I need to check all of that, like um, make my yeah. I have to use quite some wow. I'm losing my words, but like uh, yeah, uh, boy, I forgot the word for the condos, I think, condensator. But yeah, I think I can properly design good filtering for the current from the buck converter. I mean, the current was pretty smooth on deploy, so I will see if like I can also have that. And one feature I'm gonna have to add on the next flight computer is um, understanding like the battery voltage. So using a voltage divider and properly getting like um, the battery current for both for the electronics and the propulsion. Getting the voltage of the battery is going to be really important, and it was quite noisy on deploy, so I need to look at that and see if I can fix it. But yeah, that's like that's a ton of fixes to do on the flight computer, and I don't know. That's I was expecting that, but the more I look into it, the more fixes I have to do. So yeah. All right, guys. It's been a pleasure talking to you about whatever is happening for the program and all the progress that's being made. I don't have crazy test footage right now because like I feel like people are not usually interested in software or like I mean it's more impressive for most people to see test footage. So like um, I will I will try to have as many of those like trying to get many cool shots during the development program. So yeah. Yeah, thank you. I will probably do another stream uh, when I get more progress done and like when I have really cool things to show you guys. So yeah, glad I'm glad you enjoyed it. Alright, it's been a pleasure, guys. Have a good night, everyone, and yeah, see you.